In this video, we will understand the real nature of quantum mechanics, which is one of the greatest mysteries in physics. Even now, most physicists are trying to comprehend its reality. No one has figured it out yet. The math behind quantum mechanics is simple, but understanding what it means in the real world is very hard. We don't see quantum effects in daily life. These effects dominate the microscopic world of atoms. There are many interpretations of quantum mechanics, such as the Copenhagen, many worlds, and pilot wave theory. However, the most accepted one is the Copenhagen interpretation. According to this interpretation, measurement affects the state of the system. Before measurement, quantum particles exist in a superposition of states, which is a mixture of different possibilities. When we make a measurement, the superposition of many states collapses into a single definite state. The system exists in all possible states before measurement. When we introduce the measurement, the system chooses one state out of the many possible ones. First, we will discuss some of the history behind this interpretation, and then explore the core ideas it presents. Finally, we will talk about various experiments related to this interpretation. The word Copenhagen here comes from the city in Denmark. Back in the 1920s, Werner Heisenberg teamed up with Niels Bohr in Copenhagen to figure out quantum mechanics. They did important work together. At a big conference in 1927, Max Born and Heisenberg said quantum mechanics was totally solid and couldn't be changed. Heisenberg has written the book by the name of The Physical Principles of the Quantum Theory. The Copenhagen interpretation of quantum mechanics isn't one clear idea, but a mix of thoughts from different people in the early 1900s. Bohr and Heisenberg, big names in this field, didn't totally see eye to eye on how to explain it. Bohr thought quantum behavior wasn't influenced by observers, but rather certain processes led to the behavior we see in the real world. It's not about someone watching. It's about how quantum systems naturally behave. Here are some simple ideas that are part of the Copenhagen interpretation. Quantum stuff is naturally uncertain. You can't always predict exactly what particles will do. When you zoom out and look at quantum stuff on a bigger scale, it should act like normal physics. The usual predictions should hold up. The Born rule helps us figure out the chances of different outcomes when we measure a system. It's like a guide for probability. Complementarity says that some things about a system can't be measured at the same time. You need different tests to understand everything about it. Here are more points from Hans Primus and Roland Omnes, along with what we talked about earlier. Quantum physics focuses on individual objects, not a bunch of the same ones. You can use the Born rule to figure out probabilities without needing lots of identical systems. The measurements we get from devices are like everyday outcomes we're used to. Bohr and Heisenberg thought it was fine to describe these results using regular language. One of the more challenging issues in quantum physics is how to describe both the object being measured and the measuring apparatus. Heisenberg and Bohr have differing opinions about this. This means that without affecting the forecasts, the observer is free to choose how best to characterize the situation. Bohr saw things differently. He thought that the object being measured and the measuring apparatus were both profoundly quantum. He referred to this point as the cut, and it depends on how the experiment is configured. Bohr believes that the most important thing is how we discuss these issues, rather than altering the laws that govern them. Remarks on unrecorded measurements are meaningless. Saying that a photon followed a specific path, for instance, is only significant if the experiment is designed to find and document that path. Quantum systems are described by objective wave functions. This implies that they remain unchanged regardless of who is seeing them. They are not swayed by random information or subjective beliefs. Heisenberg and Bohr had their own points of view about wave-particle duality. Bohr believed that the way an experiment was set up affected whether something was observed as a wave or a particle. He reasoned that an experiment would reveal either a particle or a wave, but not both at once. However, Heisenberg took a different tack. He believed that regardless of the experiment, the arithmetic could simultaneously represent waves and particles. He thought that the arithmetic itself included this duality. A wave function is a mathematical instrument that is used to calculate the probability of various outcomes in measurements. The behavior of the system can be predicted if we are aware of the wave function and the way that things change over time. The Copenhagen perspective holds that the wave function does not represent a tangible object. It's not an image of something tangible. Rather, it's more akin to a notion we employ to perform mathematics. The Copenhagen interpretation of quantum physics places a premium on the Born rule. Born came up with it in 1926. It is useful in determining the probability of obtaining a particular outcome from a quantum system measurement. In essence, it states that the square of a particle's wave function at a given location determines the probability of finding it there. The wave function of a system will suddenly change when it is measured. Probabilities for each outcome are provided by the wave function prior to measurement, but the likelihood of alternative possibilities disappears when we measure it and observe a certain result. Since he did not believe that the wave function existed, Niels Bohr did not use the term collapse. Nonetheless, a lot of scientists relate this idea to the Copenhagen interpretation. Heisenberg studied the wave function to show how our knowledge of a system might be expressed. Instead of calling the condition of affairs a collapse, he called it a reduction of the wave function to a new state. This new condition is a reflection of how using a gadget to measure something modifies our understanding. Quantum theories that imply the observer has some control over the outcome, such as the Copenhagen model, are commonly referred to be subjective. However, those who support this theory argue that the measuring process is purely mechanical and insensitive to the characteristics of the observer. To put it simply, observations made in quantum physics are not based on subjective beliefs. The essential idea behind quantum theory is that the observer, whether it be a person or a machine, just records what occurs. Decoherence theory was able to explain some of the appearance of quasi-normality in quantum events, but it was unable to explain the apparent abrupt collapse in the wave function. The Copenhagen interpretation of quantum physics sees it as a tool for understanding phenomena rather than a description of separate real objects. It's known as an epistemic hypothesis since it focuses more on what we now know. But Einstein had an ontic theory in mind, one that sought to find concrete, actual objects through the application of physics. The Copenhagen perspective firmly responds, no, to the question of whether we might add hidden variables to the calculations to make quantum mechanics an ontic theory. Some claim that because Einstein believed that introducing hidden variables may be effective, he disagreed with the Copenhagen perspective. However, some, like Max Jammer, contend that Einstein never fully advanced the idea of a hidden variable theory. Though he considered the proposal, Einstein decided against publishing it due to issues he discovered. The Copenhagen interpretation makes sense when we see different experiments. In a famous experiment, a cat is put in a box, and the result depends on the state of a particle within it. The cat looks to be both alive and dead at the same time, which is puzzling. According to certain interpretations of the Copenhagen interpretation, a real object such as a cat cannot be adequately described by a wave function. They propose a more intricate quantum description, including the application of a superselection rule. The two individuals in the Wigner's friend thought experiment are Wigner and his buddy, also known as Alice and Bob. Wigner places his companion into the cat-filled box. From the outside, the system seems to be both alive and dead. Yet Wigner's companion believes the feline to be living. The riddle is, why do Wigner and his companion see the wave function in such disparate ways? If Wigner's friend is on the same side as the external observer, then his measurements affect the wave function for both. On the other hand, if he is on the side of the cat, his interaction is not tracked. However, his interaction isn't measured if he's on the side of the cat. Bright and dark bands form a pattern on a screen when light from a laser or other source shines through two slots. This pattern implies that the behavior of light is wave-like. However, if you examine closely, you can see distinct spots where light is absorbed on the screen, almost like little particles striking it. However, a photon that exhibits its wave-like behavior travels through both slits and creates the pattern when it is not viewed. Similar experiments have been carried out by scientists using atoms, molecules, light, electrons, and other particles. Because of their extremely short wavelength, quantum physics implies that all objects, no matter how big, have characteristics of both particles and waves. This is particularly difficult for bigger objects. A clever experiment using two specifically coupled particles was conducted. Einstein and his associates stated in a 1935 study that you can quickly determine the identical attribute of another particle by measuring one of its properties. This appeared strange since, according to Einstein's theory, information cannot move faster than light. They established a criterion stating that a property must have a genuine value if it can be predicted with absolute confidence. Bohr, however, wasn't convinced. He said that EPR erred. You cannot correctly measure the other attribute of these particles if you are measuring the first one. Thus, their conclusion on the two characteristics' specific values was erroneous. Unlike what EPR said, he thought that quantum theory was complete. Einstein was a fervent believer in the existence of an objective reality, where objects exist apart from their observation. Conversely, Bohr and Heisenberg contended that a physical quality could not be fully understood in the absence of measurement. Einstein disapproved. In a well-known tale, Einstein inquired as to whether someone thought the moon existed just because they could see it. Though he believed quantum physics to be incomplete, he did not deny that it produced correct predictions. In order to demonstrate that attributes like location and momentum had definite values even in the absence of measurement, he devised the Einstein-Podolsky-Rosen experiment. Many other scientists, however, did not think this argument to be persuasive. Carl Friedrich von Weizsäcker presented an alternative perspective. According to him, the Copenhagen interpretation does not imply that objects exist solely in observation. We may prevent paradoxes by making fair assumptions about what we haven't witnessed. The notion of unpredictability in nature did not sit well with Einstein. He made the renowned statement, "God does not play dice with the universe." Bohr allegedly replied, "We cannot dictate to God how he should run the world." Alternatives. Interpretations of quantum mechanics. Quantum mechanics is a fascinating area of physics, but it's a bit like a puzzle with different interpretations. One of the main ones is the Copenhagen interpretation, which says that particles exist in many states until we measure them, and then they choose one. Another one is the ensemble interpretation, which says we can only understand groups of particles, not individual ones. Then there's quantum information theory, which has spawned ideas like cubism and relational quantum mechanics. Even though there are these different views, a lot of scientists still stick with the Copenhagen interpretation. But some have changed their minds over time, maybe starting with Copenhagen, but later liking hidden variables or ensemble interpretations better. It's a bit like different flavors of ice cream. Everyone has their favorite. Some smart folks have different ideas about how to understand quantum mechanics based on their philosophies. One idea, called the many worlds interpretation, says there are lots of universes where everything that can happen does happen. Then there's objective collapse theory, where the wave function really does collapse when we measure it. Bohmian mechanics tries to make quantum mechanics predictable, but it brings in some weird stuff like non-locality, where things happen instantaneously over long distances. Even though some famous scientists like John Archibald Wheeler started with the Copenhagen interpretation, they changed their minds later. Wheeler still thought Copenhagen was good though, Some scientists want to dig deeper and build quantum mechanics from scratch instead of just accepting it as it is. Thank you so much for watching. See you soon again in the next video. Until then, as always, keep looking up and dream big, and good night.